तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we saw how a volume element transforms. We said that small dv is the volume of the element after it transforms, and we said that dv is equal to j d capital V, and j was the determinant of f. If j is equal to 1, or if and when j is equal to 1, then d small v is equal to d capital V. We say that there is no volume change, or the material is incompressible or isochoric. So we stopped there, and we wanted to look at now the transformation of a surface. Transformation of a surface is very important because we know that the stresses are defined through the areas, and hence the surface definitions and how it transforms are going to play a very great role in our further definition of stresses. So what we are interested in now is that, suppose I take that's the body, and I take a surface. Let's say that is the surface. Okay, let me call this area of this infinitesimal surface as ds, and let n be the normal to it, so that the vectorial form ds can be written as n ds. So this ds is the area, and this ds becomes the representation of the area along with the normal n to it. Now let us define dx such that we can calculate the volume dv formed by ds and this dx. In other words, dx dot ds gives the volume of the body, a small infinitesimal body formed with ds and dx. Right? Is that clear? Now let us say that this surface, due to the transformation, gets transformed to small ds such that the normal becomes now small n, and now the surface can be written as ds is equal to n d small s. And we are writing in the similar fashion, only thing is this is after transformation. The body has transformed, it has become like that, and now we are looking at this surface where we are concentrating. Please note, all of them are infinitesimal surfaces. The corresponding dv that is formed due to the transformation of the vector dx, which now becomes, say, d small x is equal to d small x dot ds. Is that clear? So the corresponding transformations are written here. Now we know that small dv is equal to j d capital V, or in other words, dx dot ds is equal to j times d capital X dot ds. Is that clear? Okay. Now this is small, that is the. Now let us replace dx by, we know dx is equal to f dx, and so let us replace that, so that this becomes f dx dot ds is equal to j times dx dot ds. Right. Now using the transpose, or definition of transpose, that can be written as f transpose ds is equal to j times dx dot ds. comparing, now look at that, there is a dx here and there is a dx here. Okay. Obviously then what is here to the right of this dot product should be equal to j times ds. Of course this is vector. So in other words, from this it is clear that f transpose ds should be equal to j ds, which implies that ds is equal to j f inverse transpose ds. In other words, this means that n ds is equal to j f inverse transpose n d capital S. We are not cancelling ds, we are just writing down d, yeah, dx, of course, because this is a dot product, right, of the dot product. And the two dot products, I mean, this comes from the uniqueness of dot products. So obviously, okay, you can see that you can write the right hand side of the dot products we are comparing. Now this is the celebrated nonsense formula. One of the most important formulas in continuum mechanics will be used later by us for definition of stresses. Is that clear? Okay. So having talked about now the definition as well as the transformation of surfaces and the volumes, let us now look at a very important theorem called polar decomposition theorem. Polar decomposition theorem has its origin in linear algebra. In fact, people who are interested in looking at more about polar decomposition theorem, linear transformations and so on, can refer to the book by Bowen and Wang, on linear and tensor algebra. So what I want to state, number one, very important thing is that polar decomposition theorem is not peculiar to continuum mechanics. Okay, it comes out of the result of linear mappings or transformations, okay, which is the subject or which is the topic in linear algebra. So before we state this polar decomposition theorem, we have to state a very important lemma, which I am not going to prove, okay, but very simple to understand. What this lemma states is that for any symmetric second order tensor T, for any symmetric second order tensor T, there exists a unique symmetric second order tensor, positive definite second order tensor, okay, such that T is equal to u squared. So T is actually symmetric. We should add that also, positive definite. We had already defined what is positive definite second order tensor. There exists a unique u, which is again symmetric positive definite, such that u squared gives you T. With that in mind, let us define the polar decomposition theorem. Polar decomposition theorem states that for any non-singular, that means f, if I say f is one of them, second order tensor, that means that its inverse exists. If I take a tensor whose inverse exists, then this tensor, second order tensor, can be multiplicatively decomposed into Ru, that is or is equal to Vr, we put that small Vr, where R, this R is an orthogonal tensor, and U is similar to what we have defined here, a positive definite symmetric second order tensor. So in other words, what it means is that given any second order tensor which has an inverse, I can multiplicatively decompose it into an orthogonal tensor and a symmetric positive definite tensor. Yeah, what is orthogonal tensor? We had already defined. So R transpose R is equal to I. That means that R transpose is equal to R inverse. Okay, this we had seen. For example, the case of Q, when we defined. Remember when we defined Q? Okay, we defined this to be an orthogonal tensor. One of the important properties of this kind of orthogonal tensors is that when you transform, when you use them as the transformation tensors, then the lengths do not change. Remember that this is one of the tensors which define the rigid body motion, rotation. Of course, there is one more, say, translation which can be defined by means of our CT, say, or C, a vector which does translation, right? So this is a very, very important theorem. Though I had put here the symbol F, R and U, I am going to continue with these symbols. Okay, but this is a very important theorem and can be used, as I said, generally for any other purpose also. But in continuum mechanics, the decomposition is applied specifically for F, the deformation gradient tensor. Not only is that we can decompose, but we can decompose that uniquely. In other words, F if can be written as R prime U prime, then R prime is necessarily is equal to R, U prime is necessarily equal to U. So they are unique. Okay, let us prove the theorem and look at the implications and see why this theorem is important. Right? So first let us prove the theorem in the sense that we are going to show. First part is very simple. We are going to show that you can write it in this fashion, and the second part we are going to show how this decomposition becomes unique. So, is any questions?
Sir, is that R and U are the rotation gradients and displacement gradients?
No. I will talk about that in a minute. Okay, let me just wait for a few minutes. You are absolutely right, but let me first prove it. We will look at the physical picture. It's a beautiful physical picture will evolve out of this decomposition. You have to wait for some time. Okay, so let us go ahead and now first prove the theorem. Let F transpose F is equal to U squared. Let F transpose F is equal to U squared. Obviously, I can assume like that because my F transpose F qualifies my theorem, the first lemma which I stated. So obviously, I can say that let F transpose F is equal to some U squared, okay, and F transpose is equal to V. Okay, both of them qualify, sorry, V squared. Both of them qualify, okay, for the first lemma. Is that clear? Now, let R be equal to F U inverse. Let again. Then my first job is to show that R transpose. First job is to show that R transpose or R transpose R is equal to I. Okay, if I define like that, is this R orthogonal? Please check up. R transpose is equal to F U inverse. So again, F U inverse transpose. So that becomes F U inverse transpose F transpose. Okay, U being symmetric. So F U inverse F transpose so which is u squared, so f u squared, okay, f transpose, which, okay, according to our definition now becomes what? Is equal to I. So in same way you can show that R transpose R is equal to I. Okay. So in other words, if I define f like that, then my, in fact, R transpose R also becomes I. So in other words, when I define like this, then R becomes an orthogonal tensor. So obviously, now if I define U to be like this and R to be like this, then it's quite straightforward that my decomposition of f R U gives me an orthogonal tensor and a symmetric tensor, okay, both of them second order tensors. Now let us see how we will see the decomposition of the second one later. Let's see how we can prove the uniqueness. If you want, you can write down right away yes also to be, say, let us say yes to be equal to f, we defined f is equal to VR, and so let us say f we defined, s is defined as V f inverse, okay. We can again show very easily, straightforward, that s is again an orthogonal tensor. Let, I am saying let. Now my job is also to prove that s is equal to R, okay. I will do that later, okay. So the second part of the story, we will just keep it for a minute. We will first prove the first part, f is equal to Ru, by showing that R has to be unique. So in other words, what really it means is, as I told you, if I write f is equal to Ru, that is equal to R prime U prime, then R prime is equal to R and U prime is equal to U. It's very simple. C is equal to, say, f transpose f, we know that, right, and that, write it down in terms of this, f transpose f. So that means that U prime transpose R prime transpose R prime U prime. So what happens to this? So this goes to I, so that becomes U prime squared. We already know that f transpose f is equal to U squared, that's how we had started the whole thing. So this becomes U squared. So U prime squared is equal to U squared, which means that U prime is equal to U. So once U prime is equal to U, obviously this condition gives me the fact that R prime is equal to R. So the decomposition is unique, right? Okay. The next point is very simple. Suppose I write this, what I am saying is, let us write that as Vs. Let us look at the second part. Vs is equal to Ru okay. So from this we have to show, this is equal to f, of course, we have to show that S is equal to R. How do we show that? Just think about it for a minute. S is, of course, an orthogonal tensor that is there. So see how we can show how S is equal to R. Ru. It's quite simple. So let me say f is equal to Ru, that's equal to S S transpose R U, S transpose R U, okay, and then that is equal to I, or you can in fact write it slightly different fashion. You can write F is equal to S into S transpose V here, S, okay, that we can compare that with RU. What essentially I have done is S transpose equal to I, so this one first I have just pre-multiplied by S transpose, okay, so this becomes I, and that is equal to RU, okay, so both the equations are the same, which means that since the decomposition has to be unique, okay, this R has to be necessarily equal to S, and this U is necessarily equal to S transpose Vs. So U is equal to S transpose Vs. So what I essentially did was to just pre-multiply this by I, or in other words, F is equal to Vs, and that is equal to IVS, that is equal to S transpose Vs, and from there I got this relationship, okay. So it's a very straightforward way of showing that S is equal to R. So final result I'll write here, F is equal to RU, that is equal to VR. Right. Now just to understand what this U is, what this R is, let us now look at the definition for our stretch and whether we can use this decomposition at that place, right. Is this clear? Any questions on this? Okay. So we will now show what is the physical meaning of this. Please write down the stretch equation from your notes and substitute there this decomposition. Remember what was the stretch, say lambda of say m, we wrote like that, if you remember, okay. So that was m dot F transpose F m, please go and have a look at what, yeah, correct, whole power half. This is how we wrote, right. This is d small x by d capital X, mod of them. This is dot product. So what is this? What is this from what we had defined now? U squared, very good. So U squared. So this can be written as m dot U squared m whole power half. And what is that? That is nothing but the magnitude of um. Now what does this indicate? What does this indicate? It indicates that if I have a material line element dx, okay, the stretch part of the material line element has only the u part of f, and hence the lengths are affected only by u, only by u, okay. So if I have now f dx which is equal to ru dx to give me that small dx, what it really means is that this dx is stretched by the u part of f, and then in other words this fellow now undergoes a stretching, okay. Stretching is I mean expansion in length is one of the conditions of stretching. Stretch doesn't mean that I'm looking at it all the time. Then this guy gets rotated by r, say, to become like this. So this now is d small x. So this transformation f involves a stretching followed by a rotation. Okay, is that clear? So F cannot be treated, look at this very, very carefully, F cannot be treated as a measure of strain. Now go back and look at my definition for strain. What was my definition for strain? Say E. E is equal to half F transpose F minus I. Very good. Now, what is the connection between this U and here? This is equal to half into U squared minus I. Now look at this condition here, what we had written for E. What has happened there? We have actually been very careful in defining the strain to be one which is affected by stretch or by U alone. Okay? So this is called pure stretch because U does not contain any R in it. Hence, the strain is not affected by the rotation part of it, but is affected only by the stretch part of it. Okay? In the same fashion, when we defined Almancy strain, what did we do? We did that as F inverse, remember that I minus, what did we do? I think if I remember right, I used small e, half into I minus F inverse transpose F inverse. Okay? Now you will see that this is V inverse squared, and hence we see that this again depends upon the stretch. Okay? So when, on the other hand, when you use Vs or Vr, what it simply means is that first you rotate it and then apply the stretch. Rotate it and apply the stretch. So by this decomposition, we are clear about that component of F which causes stretching and that component of F which causes a rotation. Yeah, see what we mean to say is that suppose I have, let me explain that again if you have a doubt. Suppose this is the body, okay, this body undergoes transformation, so it goes like that. So that's the point x, okay, so that point becomes small x, and let us now see what happens to this material line element, say dx. This undergoes a transformation first to a body like that, or yeah, body like that, so that dx now becomes u dx, which is the stretching part, and then that gets later rotated from here to here, so that becomes r u dx. Okay, so there is a stretching first followed by rotation. Stretching followed by rotation. If it is Vr, then it is rotation followed by stretching. Okay, fine. Note that again this is different from the decomposition you would have done for ui comma j in the small strain case. We are going to see an equivalent of it maybe in this class or next class, that ui comma j, if you remember ui comma j, you would split it up into a symmetric part and a skew symmetric part. So the skew symmetric part you would have called that as omega, and that was called as the spin tensor, okay, or spin, just this omega, which is half of ui comma j minus uj comma I. Okay, that's a skew symmetric part. So you would call that a spin. So you might have a doubt, what is that omega which was something like a spin, a rotation, and what is the difference between that rotation and this rotation? Interestingly, you will see, okay, in a minute, or maybe later in the class, that this spin has something else attached to it. It is not pure spin, this spin here. and that this R is a pure rotation. Okay, we will see that in a minute, so don't get confused now, we will sort it out in a minute. Is that clear? Okay, having defined now the decompositions and RU decomposition as it is called, let us come to one more decomposition called spectral decomposition. Now, what is spectral decomposition? I think we have done that, or you would have done it in earlier classes. On eigenvalue problems. All of you know that if I have, say, a tensor T, then there exists, okay, for a symmetric second order tensor T, there exists a Vi such that Vi is equal to lambda I, and you know all the properties of Vi, and which you would call as the eigenvectors, and lambda I you would call this as eigenvalues. Okay, I am not going to the details of all this, I am sure all of you know these things, we had covered it in the first course and you would have studied that in linear algebra. In other words, what I just want to emphasize is the fact that T can be written as sigma lambda I Vi dyadic Vi. So in other words, this Vi dyadic Vi I is equal to say 1 to 3 can be used as the basis, or eigen vectors can be used as a basis for definition of any tensor. So in other words, when the basis is shifted to these eigenvectors, then T can be written as say lambda 1, lambda 2, lambda 3, the others being 0. Is that clear? Okay. Of course, the question is what happens when lambda 1 is equal to lambda 2, then how do you write this? How do you write this? So you say, for example, lambda 3 is unique and lambda 1 is equal to lambda 2, then what is the condition of the eigenvector? Then any two, yes, absolutely. So any two perpendicular vectors, okay, in a plane which lies in a plane defined by the lambda 3 to be normal, or V3 rather to be normal, will qualify for an eigenvector. Okay, we can define this using a projection theorem, as it is called, okay, in a very simple fashion, and maybe we will go into the details of this when we come to it, maybe in the next class or so. So now the point is that having so many tensors, okay, is it possible to get their eigenvalues and use that for any of this analysis? That is what is done in many cases, and many of the analysis are based on what are called as principal stretches. Principal stretches. So in other words, in the same fashion as we define the eigenvalue problem, this T can be replaced by my U, okay, and UMA, remember that UMA was the guy who was in my stretch, okay, remember that's what we ultimately landed up in a few minutes back. So I can define an eigenvalue problem, okay, using U, because it is the symmetric second order tensor, into lambda say AI MA. So this gives rise to, this problem gives rise to 3 eigenvalues, and 3 eigenvectors, lambda say a1 or lambda 1, lambda 2, lambda 3 if you want, and write this as m1, m2 and m3. I put that as a for a particular m because you remember that m we had used it previously to denote any unit vector. Okay, so this is a normalized version, that's all. If you want to remove it, you can remove that. Okay, there's no harm in it. Just to distinguish that m is not any vector, so that's why I'd put it. But if you know the context, then obviously you can remove it and you can write it something like that. So what happens to, what is the relationship between the eigenvalue and the eigenvector of u and C? What is C? C is F transpose, remember what is C? Right Cauchy, so F transpose F, F is in the right hand side, and so that is equal to u square. So what happens now if I put u there, u of um? So in other words, u squared of m, what happens? Lambda squared. So u squared m of I is equal to lambda squared, u of again lambda mi. So lambda I squared mi. How did I get that? It's very simple. If you don't understand it, I'll put that step again. U of u mi is equal to lambda I u of mi. Okay, so this becomes u squared mi is equal to u of mi substituted from here, so that becomes lambda I squared mi. So in other words, the eigenvalues of C, the square of eigenvalues of u and the eigenvectors do not change. So these lambdas are called as the principal stretches, and many, as I told you, many elasticity problems people indicated or use what are called as principal stretches. So principal stretch is again one of the ways of defining strains. In fact, I should have mentioned it, that a general way of defining strains, is by putting 1 by m u power m minus I, where m takes the different values. So for example, m takes a value of 2, this equation reduces to our well known Cauchy Green strain. When m is equal to 0 or m is equal to 1, then this reduces to u minus I. Okay, so this is also one of the strain measures that are used. In fact, another strain measure that is used is ln or natural logarithm of u and so on. So these are generalized, other generalized strain measures. Okay, we may not use all of them in this course. Okay, when it is necessary, I'll define it. But I just want to state that E, there is nothing very holy about this E definition of capital E. You can define, okay, various stress measures by using various powers of U as well. Okay. Now, so this again, one of them is the principal stretch. The advantage of principal stretch is that immediately my stretch would be just a diagonal lambda 1, lambda 2, lambda 3, and they are the stretches along what are called as the directions of the eigenvectors. Now, having done that, what is the relationship between this principal stretches of u and v? Is there any relationship between them, between the principal stretches of u and v? Remember that v is a measure which can be used along with Almancy strains. That means that when you are dealing with the current or deformed coordinate system, which means that you are the Eulerian coordinate system, then the measure that you would use is Almansi strains. And so it's important that we also understand what is this relationship between the lambdas of u and lambdas of v. Are they the same? Are they different? And how the eigenvectors also gets transformed. No, you don't guess. Please look at it. Please look at this. Go from here. Okay, go from here. No, wait a minute, don't be in a hurry. So just multiply this by r is equal to lambda I r mi. Okay, Ru is equal to Vr. So V of r mi is equal to lambda I r mi. Now look at this expression here. That talks about the eigenvalue problem or eigenvalue equation of V. Right? The only thing that has changed here is that this m has become Rm, and hence the eigenvector has now become Rm. So eigenvalue here has remained the same. So what does it mean? It means that the eigenvalue of V, or the principal stretch or the principal values of V, is the same as that of my u, but the eigenvectors get transformed, okay, or is rotated by r. Is that clear? Okay, so that's another important result that we have to see. Please note that similarly C has lambda squared as their principal stretches. Having defined now these quantities, which I will use it later in the course, we have to define quantities, or we have to calculate what are called as rate quantities. What is a rate quantity? Which means that how does many of the quantities what we are looking at now will change with respect to time. Rates in continuum mechanics. What is the big issue there? You may think, but there are quite a few issues which we have to sort out. What do we mean by rate quantity? Suppose I have some function f of t. Obviously what I am interested is in f dot. Okay. Now what is the issue here? The issue is that this quantity f may be a function of small x or maybe a function of capital X. When f is a function of small x, then they call this as spatial time derivative, and when f is a function of capital X, they call this as material time derivative. Spatial and material time derivative. Suppose now I write that f as a function of x comma t. Okay. Note that if this x can be replaced by capital X by my deformation function t. Or in other words, the issue is that when I define the Eulerian coordinate, that Eulerian coordinates, okay, that small x now changes with time, but whereas the capital X, which strictly speaking is our reference, first time when I marked it, it was there, that doesn't change with time. Okay. So you can look at the derivatives in two aspects. One is the material derivative of a spatial function, okay, material derivative. That means that how does actually this particular quantity is going to transform, okay, or going to or how do I take the rate quantity of a spatial time derivative. So in other words, is it that dou f by dou t is equal to f dot, or is there something more to it? Something more to it. Very good. So what is that is what we are going to see. Okay. So maybe we will derive that in the next class and then derive certain quantities which are associated with the spatial and the material time derivative and what's its relationship in the next class. The only thing I just want to point out that usually the material time derivative is written with a capital D df by dt, and spatial time derivatives are usually written as dou f by dou t. Is that clear? Now, before we go to the derivation, yes, I'm going to derive that in the next class. Don't have enough time. So there's one comment I want to pass is that many of the constitutive relationships which we are going to use these rate quantities. Hence, determination of rates become very important. You understand that the determination of rates become important. So we have to necessarily know how to calculate this and distinguish clearly between spatial and the material time derivative. Okay? So we'll stop here if there are no questions. We'll stop here and continue with this derivation in the next class.